important stuff, because this is where we start getting into, well, I already said it, applications of the derivative. But the thing is, it's kind of unsatisfying in the sense that what textbooks call applications of the derivative really actually have nothing to do with applied math. It has more to do with just actually using the concept of a derivative to get other answers for other types of questions. All right. So that's what we're going to get into here. But we need to talk about exponential functions and logarithms first, because a lot of the stuff that we do involving implicit differentiation comes back to what we call transcendental functions. Transcendental functions, you've seen these before. It's just a kind of a fun term, and you would not necessarily think that it would be a straightforward idea just by the name of it, transcendental. But really, it's just saying anything, any form of math that transcends ordinary algebra. So exponential functions, logarithms, trig functions, things like that, where ordinary algebra rules wouldn't necessarily apply. All right, but what we want to do to get started is find the derivative of f of x is equal to e to the x, and we're going to go right back to that limit process. The fun thing about this idea, or at least finding the derivative using the limit process for exponential and even logarithms, is the fact that it's actually a whole lot easier than doing it for some of the algebra problems that we were working with. So again, limit as h approaches 0 of f of x plus h minus f of x all over h. And again, just to drive this point home, this piece of the limit definition gives you the slope over an interval. All right, so just a quick refresher. We have, you hear? That's math teacher talk, not student on a test talk. We have the function f of x is equal to e to the x. All right, if I wanted to find just this piece, what I would be doing is starting off at some point on my graph and finding the slope between that point and some other point on the graph. But then what we would do is move that second point closer to the first point. Find that slope. Then move that point, that second point, even closer to the first point. Even closer. We still have that fixed point here that we call A, but that second point is getting ever closer to the first point. All right, because we can't find a slope between a point and itself algebraically, but we can figure out what these slope values are approaching. All right, they're clearly getting smaller and smaller. It's just a question of getting smaller and smaller to what? Getting smaller and smaller to whatever the slope of the tangent line is at that point. All right, so then what you would do once you find the slope at that A value is you'd move on to another point. You know, move A a little bit further down the line and repeat the process. And then what you would end up with are different slope values. Those slope values together give you a function. All right. So that's what the limit process gives us, the idea that the second point is moving ever closer to the first point. All right. So in this case, we know that f of x is e to the x, but f of x plus h would be e to the x plus h. So e to the x plus h minus e to the x all over h. That's what we're looking to limit. All right. Now this piece right here, this is where the magic happens. All right. You might remember keep the base, add the exponents. So if I had something like, let's say 2, for example, 2 to the 3rd power times 2 to the 4th power. Keep the base, add the exponents. I mean, I could write it in general terms, but I think this gets the idea across, right? So instead of going from here to here, what we're actually doing is going from here to here. We're working backwards. So e to the x plus h would be the same as saying e to the x times e to the h. And everything else would remain the same. All right. The benefit of doing this is the fact that we can now factor out an e to the x from this fraction. So we'd have limit as h approaches 0 of e to the x. When you factor that out, you're left with e to the h minus 1 over h. Now, since the e to the x is irrelevant to the limit, it's a factor that doesn't involve an h, we can factor it out of the whole thing. So e to the x times limit as h approaches 0 of e to the h minus 1 over h. Now, at this point, because we haven't learned L'Hopital's rule yet, and we'll learn that in about a week. So we got to kind of sit tight a little bit longer. We just have to take it on faith now that this by rule is equal to 1. So it's equal to 1 by rule. Whenever you write an equal sign with 3 bars, it means that it's equal by rule, right? It's not equal because we computed anything. It's equal because the rule says that it's equal, all right? So let me just show you really quickly on Desmos, f of x is equal to, and I'll just use e to the x instead of e to the h, minus 1 over x. As x approaches 0 here, coming in from the left, coming in from the right, we can see that it's approaching this location, which is undefined because there's a hole at that location. But it's pretty clear that it's approaching a location, even though it doesn't exist along the curve, that y value is clearly a 1, all right? So this isn't a proof, it's a justification. We'll get to the proof down the line, but that allows us to say that the derivative of e to the x is equal to e to the x. So that's f prime of x, all right? So if I say, here's my function, f of x is equal to e to the x, all right? So my normal function, e to the x, well, not normal in the normal curve sense, but normal as an ordinary function. I could find its derivative graphically just by simply typing f prime of x. And you see that they map to the same location. All right, I'll make one a little bit thicker so that it's more obvious, and I'll even dash it up. All right. So now you can see that we're looking at 2 graphs that are identical. All right, they're living on the same coordinates. So that's a justification that the derivative of e to the x is e to the x. But then you see this fun notation here at the bottom, the rule. It's the chain rule variation of the e to the x rule. It allows for the exponent to be something other than x. All right. So if I follow this rule, so I let u equal, all right, that crashed. In case you wanted to know what my Algebra 1 test looked like, I already took it today, so the secret's out there. All right, we got that one. Yeah, we get back there. So if I let u equal x, I'm saying the derivative with respect to x of e to the x power. Right? If I follow this model, I'm going to say that the result is e to the x times, instead of du, I'm going to say dx dx. Now, dx is kind of weird because you look at that and say, well, what does that tell you to do? Well, it doesn't really tell you to do anything. It's it's the noun-verb relationship. Sometimes notation tells you to do something, and sometimes it just tells you what it is. Right? In this case, dx can be thought of as a ratio. That ratio has the same number top and bottom. So if I said we have a fraction 2/2, you'd simplify that to a 1. So it wouldn't be any different for dx. That goes to a 1. And even by this rule, we still get e to the x as the derivative of e to the x. All right. But it allows us for more to work with more complicated situations. So for example, and honestly, this really should be an example in the notes, so I'll take it as a typo. The example, let's say we have d dx of e to the cosine of x. All right, let's say that that's what we were looking to find the derivative of. Not, something a little spicier here. That would give us the u value, so let u equal cosine of x. So by rule, we would be saying e to the u, so e to the u is e to the cosine of x times du dx. Well, the du dx, well, I can look at my expression here and say, okay, well, what is du dx? Well, let's figure it out. Du dx, cosine of x has a derivative of negative sine of x. So my du dx would be negative sine of x. And that would be my derivative. So if you're looking for a kind of a more shorthand way of thinking about it, it would really be a matter of saying, if you're given an exponential e expression and you need to find its derivative, rewrite the exponential e, whatever the original expression is, and then just multiply by the derivative of the exponent. Right? It's actually pretty simple when you think about it that way. But it's also another rule to know. So, it's not ideal, but it is manageable. Okay, but things like constant multiple rules, those are still going to be in play. So when I'm looking for the derivative of 3e to the x, I can look at it as 3 times e to the x, and the constant multiple rule tells me that I can hang on to the 3, take the derivative of the e to the x separately. Derivative of e to the x is e to the x, and there you go. All right, so that one's not too bad. Next one's actually even easier because the first part, it's really just a justification, a justification of the sum and difference rules for derivatives. We take the derivative separately. Oh, by the way, the word of the day is honesty. Okay. So honesty is the word of the day. So derivative of e to the x is e to the x. Negative 3x to the 6th, that's power rule. So that's going to be negative 18x to the 5th. Use my color code. So that's not too bad. I mean, it's not bad at all. It's pretty easy. The next few problems involve a little bit more oomph. So we got a little bit of quotient rule, product rule, chain rule going on here. For quotient rule, low d high minus high d low over denominator squared, and away we go. Concepts that'll never go away. So low is x, d high, derivative of e to the x is e to the x, minus high, e to the x, d low, derivative of x is 1, over the denominator squared. And away we go, of course. Now, if you wanted to simplify this, you could, but these questions aren't asking you to do that. Any skills-based questions is going to be just the kind of question where you would not need to simplify. So the question I'm seeing is, so e to the x will always be e to the x. Yes, derivative of e to the x is e to the x. So if you needed to go further, On this one, you could factor out an e to the x, and you'd be left with x minus 1 over x squared. All right, so you can simplify a little bit further. We will get to a point where we're going to want to simplify just for the sake of making our lives easier when we answer follow-up questions, but it's not something that that I'm going to mandate for any skills-based question. All right, so f prime of x in number 4. Little product rule. First, I could zoom in, but I wanted to keep the whole screen. It's x to the third times the derivative of the second, derivative of e to the x is e to the x, plus the second, e to the x, times the derivative of the first, 3x squared. Another situation where you wouldn't need to simplify if it's just a skills-based question, but I'm going to show you what the simplified form would look like anyway. We have a common e to the x, can be factored out. We would then have x to the third plus 3x squared, but then you might recognize that we have a common x squared that can be factored out. So x squared e to the x times x plus 3. All right, so any of those variations would be, they're all equivalent, so they're all fine. All right. Next up, we have a little bit of chain rule going on. All right, we have a function contained within another function. All right, so what I'm going to do here is redefine this as y equals u to the third power, where u is equal to e to the x minus 4. All right. Derivative dy du, poor quality y, fix that, is 3u squared. Du dx is equal to just e to the x because -4 cancels away. Derivative of -4, it's constant, goes to 0. If I multiply these two expressions, the ratio dy du and du dx, the result would be dy dx. So I'm going to take this and multiply it by this. So 3u squared, but I know that u is really e to the x minus 4. So I can make that substitution. All right. Which actually brings us to, it's kind of a shortcut, but there are some mental gymnastics that need to happen in order for you to follow the shortcut. When it comes to the chain rule, if you just kind of imagine the u instead of actually explicitly writing it, what we do is we take the derivative around the inner function. So I would look at this as, instead of e to the x minus 4, I would say that that is something to the third power. You know, some expression raised to the third power. So if I were applying the power rule to some expression raised to the third power, what would I get? I'd get 3 times that expression raised to the second power. Right? Then all I'd have to do is remember to take the derivative of the inner function, whatever the inner function is. Right? So let me just show you really quickly, because it's not, it involves a lot of hand waving. I'll put this back in a second, but I just want to show you real quick. So a lot of people don't like it, but I'll show it to you anyway. So I would look at this and say, all right, we got something raised to the third power. So how would I find the derivative? 3 times that something raised to the second. And then I would reveal the something. Okay, well, it wasn't just something, it was actually e to the x minus 4. So then I would take that derivative and multiply it on at the end, which would be e to the x. And so that would be my f prime of x. All right. The shortcut kind of, I mean, I don't want to say it falls apart, but it's not as cut and dried when you're dealing with multi-layered expressions. So function within a function within another function. So, you know, some people kind of like, they prepare for the worst and hope for the best. They say, all right, I'll try to do it this way, but if it doesn't make sense to me, I can always default back to the other way. All right, but I figured at some point I probably should show you that. And so here we are. All right. So you could actually apply that same reasoning to the next one. I would say, all right, we got something to the third power. What would my derivative be? It would be 3 times that something raised to the second power. Now for the reveal, that something, well, guess what? It's actually e to the x. So take the derivative of the e to the x and tack it on at the end. All right. You
Well,
could do
Professor,
it that way. Yeah.
why are you tagging it to the end?
Because whenever you take the derivative involving a chain rule, you have to take the derivative of the outer function and also the inner function. So whatever the inner function is, we have to find its derivative and then multiply by whatever that derivative is. It just makes sense to put it on at the end because it keeps it clean. All right. So another way to handle it would be to say, okay, well, I have y equals u cubed, where u is equal to e to the x. And you just think about what we're doing here. I'm taking the derivative of u cubed. That would be dy du is equal to 3u squared. Well, that's really what I did here. If you think about it, 3, the u is really e to the x squared. So we're actually covering all of that in the shortcut and also in the longer approach. So du dx has a derivative of e to the x. That corresponds with this piece. All right, so when you put it together with our substitutions, we'd have 3u squared, with the u being e to the x. And then we're multiplying it by e to the x. All the shortcut method does is it allows us to accomplish that a little bit quicker. All right. There's actually a third way to do that, and that involves you multiplying the exponents and applying this rule up here. But I'll leave that to you to try. It's because the next one is going to kind of get that idea across anyway. Right. So f of x is equal to e to the 3x minus 2. If I'm following this model, d dx e to the u is equal to e to the u times du dx. In this case, it's very close to being that model, except u is equal to 3x minus 2. Right? So du dx would be equal to 3. And so if I'm looking for the derivative f prime of x, it's supposed to be e to the u. The u is 3x minus 2, so e to the 3x minus 2 multiplied by du dx, which we just determined to be equal to 3. So that actually is the chain rule. Just it looks a whole lot different from all the other chain rule problems that we've done. But if you look at that e to the 3x minus 2, and just kind of imagine it's similar to numbers 5 and 6, where we would say, all right, instead of e to the 3x minus 2, it's e to the something. All right, well, what's e to the something? The derivative of e to the something is e to the something. Now, if I just remember to multiply by the derivative of the something, whatever that exponent is, then I'll have my answer. All right. So you can actually jump right to it very quickly by saying, again, e to the something power is going to be e to the something. All right. Now time for the big reveal. The something is really x to the 6th power. So then I would just multiply by the derivative of that something, which would be 6x to the 5th. All right. it's just a shorter way of doing this process here. All right, so if you like it, do it. If you don't, because you always have that other approach to use. Number 9 is actually a trick question because it's got an E in it. So it's designed to make you think that it's an exponential function, but this is actually a power relation. So f of x, I'm rewriting f of x, 1x to the 7e power. You would treat that the same way you would treat like 3x squared. Multiply the power by the coefficient. So 7e x, and then reduce the power by 1, 7e minus 1. And that would be my f prime of x. So I figured I'd throw that in there in the notes just to kind of give you an example of how a problem might look that involves an e that would not necessarily be an exponential function. And I can actually show you really quickly. We know what exponential e looks like. Right? It has a horizontal asymptote and increase dramatically. Right? So if I show you y equals x raised to the 7e power, you got this thing going on. And it looks like it might have some of the same characteristics, but it also really kind of, to some extent, really doesn't, because if you follow this graph, it comes to a dead end here and it doesn't extend beyond. Right? There's no instance in which you would ever get something that's continuous, but also in the negative direction. Right? So this is definitely not an exponential, although it does have some characteristics that make it seem like it is. It definitely is not. It actually is a kind of well, it's more than kind of, it's a composite function between a power function and an exponential. All right. So we're going to look at logs now. And it's like, oh man, we're just getting the handle on the exponential function. Slow down, dude. The only reason I feel comfortable jumping into this is because it actually relies on what we just learned. All right. So to find the derivative of a natural log involves us finding the derivative of an exponential function. So let me change the way of saying that, or rephrase. We're going to find the derivative of a log without finding the derivative of a log. All right. So for those of you who don't like logs, this might be right up your alley. All right. So if we have f of x equals ln of x, we could also write that as y equals ln of x. So far, so good. That should be the easy part. What I'm going to do is look at this and say, you know, I'm a student in the class. I don't know how to find the derivative of natural log. That's why I'm here. All right. Well, what do I know how to find the derivative of? Well, I know how to find the derivative of power functions, trig functions, and exponential functions. You might remember that there's a way to convert from log form to exponential form. You might have learned it in different ways. The way I like is log base b of e equals n. The Ben rule. I don't know. My son's name's Ben, so I kind of gravitate towards this. That's equivalent to b to the n equals e. That being said, it's a nice rule. That being said, that's not how I do it. When I'm converting from log to exponential form, I use the circular path. You start off with the base, and then you work your way around. More of a visual type person. So I would say, okay, well, it's b. B for base of a log, base of an exponential. So I know where I'm starting. and then work my way around, it's got to be b to the n equals e, right? And people, when they struggle with this, they only struggle going the other way, or mostly struggle going the other way, going from exponential to log form. But it's the kind of thing where you rarely will find yourself having to use this rule to go from exponential to log form. It's really going from log form to exponential form. Then you look at this expression here, ln of x, and you say, well, I don't see an log. We hopefully remember that natural log is the same as log base e. So this would be rewritten as log base b of x. I would then write that equals y on the right-hand side rather than on the left-hand side, so that it fits my little circular motion business here. So I would say e to the y is equal to x. So I'm done with the log. That's great. I don't like logs, so I don't have to work with logs. It's wonderful. So I'm going to write that again as x equals e to the y. Same thing, just changing the order, because I want to take the derivative of this. All right. So the derivative, when we have an equation solved for y in terms of x, we would normally write that as dy over dx. But this is the inverse of that. So we're going to find the derivative of the x equation with respect to y. The derivative of e to the y, where the independent variable is y, by rule would be e to the y. Bearing in mind that my whole goal here is not to find dy over dx, it's to find, I'm sorry, dx over dy is to find dy over dx. So I'm going to write this e to the y as e to the y over 1 and take the reciprocal of both sides of the proportion here. So I'd have dy dx is equal to 1 over e to the y. So I got dy dx. Now the original function was given as f of x. So I would change my notation here. Instead of saying dy dx, I'd say f prime of x. But then I'd be thinking to myself, I'm like, well, it's f prime of x, but I'm looking at an expression that involves y. Now that's actually okay, but we do have something that can be substituted in for e to the y. It's right here. E to the y is equal to x. It says it right there. So that tells me that I can replace the e to the y with an x because they're equivalent. So that tells me at long last, by the way, without having to use a limit definition, so that's something, right? That the derivative of f of x equals ln of x, the derivative of the natural log of x is simply 1 over x. Right? So take a look at that graphically. Ln of x. That's a good looking natural log function. F prime of x. All right. F prime of x is that blue curve. Now I'm going to graph y equals 1 over x. Oh, meh. Now you look at this and say, well, it's not right. Look at this. Wait, hold on a second. These are two different curves. There and there. This has 1, this has 2. But actually, if you think about it, the natural log function by the domain only exists because you can't take the log of a negative number, can't take the log of 0. It only exists for values of x that are greater than 0. So on the domain of 0 to infinity. So I would only care about this function if x is greater than 0. All right. So what I would do here is make it piecewise function, like restrict the domain. X greater than is what I meant to say, 0, and then turn that on. And now you see we're looking at the same graph. All right. So the relevant piece of the graph coincides. All right. We just have to know what the domain restrictions are. Natural logs are kind of weird like that. Same thing with exponential functions. Exponential function e to the x only exists for y values greater than 0. So it would make sense that its inverse would only exist for x values greater than 0. Right. So below that, we have the chain rule variation of it. So just like we did on the previous page, I want to throw in a side example. So we would say f of x is equal to, actually, let me go with the ddx notation. I want to get something good here. We're going to say ln of cosine of x. Okay. So if I follow the rule here, I would let u equal cosine of x. There would be a restriction, right? Because you can't take the log of a negative number. So the cosine of x has to be greater than 0, right? So where cosine of x is greater than 0. So we keep that in mind in case it pops up, right? Du dx is what I meant to write. It's negative sine of x. So if I'm looking for the derivative here, I'm going to say 1 over my u cosine of x times negative sine of x, which becomes negative sine over cosine, which, if you simplify, becomes negative tangent of x. All right. So let's take a look at it graphically. Look at that. That's a good looking graph. Pretty busy too. So this is what the natural log of the cosine of x function looks like. That's a pretty interesting looking graph. Right. Its derivative looks like that. Now, if I type in the negative tangent function, we got a little bit of an issue here. So the tangent function gives us more values than it's given us more than we bargained for. All right. So this goes back to this relationship here where cosine has to be greater than 0. If you think about the unit circle, ASTC, all right, going around, all trig functions are positive in the first quadrant. Only sine-related trig functions are positive in the second quadrant, tangent in the third, and cosine in the fourth. I'd only be looking for, if I'm restricting my domain, I'd only be interested in first and fourth quadrant cosine values. All right. So if we think about where that would plot in terms of an actual function, that tells me that I would be ditching anything that exists between pi over 2 and 3 pi over 2. All right. So let me show you real quick. I'll turn on both graphs. I'll make this one dotted and thicker. Let me actually make it a different color so it stands out more. kinda. Let me actually make this one a lighter color so it stands out less, I guess. And let me make this one really dark. So really, I need a contrast is what I'm getting at here. And then let's go to like 8 on this. Yeah, there we go. Looks a little bit better. All right. So let me restrict my domain so that first I'm looking from 0 to 2 pi. All right. So this is a 0 2 pi domain. All right. What I'm going to do is I'm going to draw a vertical for every one of the quadrantal angles. So x equals pi over 2. We'll make that dotted. X equals pi, also dotted. X equals 3 pi over 2, also dotted. All right. So little color coding. If we go to our unit circle, we know that as we go around, we start off at 0 radians, we get to pi over 2, pi, 3 pi over 2, and then finally 2 pi. What this is telling us, because cosine needs to be positive, because the natural log can only contain non-negative values. Well, and it can't involve a 0 either, so positive values. I would want to disregard anything between pi over 2 and pi and 3 pi over 2, which means anything from pi over 2 to 3 pi over 2. All right. So what that would tell me is that anything in this domain, let me see if I can remember how to do this. Pi over 2 less than x less than 3 pi over 2. Anything in this interval would be excluded. All right. So we would ditch that part of the graph. So since a periodic function repeats the pattern periodically so we're going from 0 to 2 pi, we know what the pattern is. We would follow that same pattern from 2 pi to 4 pi, 6 pi to 8 pi, and so on. So all of the ones that are just orange would be gone, right? Because it's telling us to exclude everything in between those intervals based off of this relationship here, right? So that's the power of the domain. We have to make sure that we're accountable to that, because if we're not, then we end up getting more information than we would really want, and more information than would actually be appropriate. Right? But when it comes to actually computing derivatives, it's not too bad. It's just you do have some domain considerations that you'll have to make. And in this case, it would be just making a note of whatever the domain is of the inner function. So the fact that I noted here that cosine has to be positive covered me, so that when I'm dealing with my derivative, f of x, or sorry, I use d dx here. So d dx of ln cosine of x would have a derivative of negative tangent of x with the notation that's supposed to be a semicolon. I can't make a semicolon without it looking like a J, so apologies. Such that, or semicolon, cosine of x has to be greater than 0, right? So that stipulation would be required. However, when you're dealing with linear functions are everywhere continuous. So it ends up being a lot easier to pick out, because all I'd have to do is look at this and say, well, I'd only care about the natural log function where x is greater than 0. So that's consistent with the domain of the original problem, the original derivation. All right. So in this case, it's just f prime of x is equal to 4 times the natural log of x's derivative, so 4 times 1 over x. All right. But then we would also say where x is greater than 0. All right, so this part of it should become kind of second nature, where you're just kind of tacking it on to the end in most cases. But when it comes to trig problems, you have to account for it in different ways. Oh yeah, very good. So the question was how to do primes, and the answer was create the apostrophe and teamwork. Very good. All right. So then a lot of these other problems are kind of similar in terms of the approach. So I'll leave these for you to try, but I wanted to take you through number 7, and that's where we would end it. So we'll do number 7. I'll leave these problems. I'll throw stars on them for you. But for what value or values of x does x squared ln of x have a, horizontal tangent line? What we would do is first take the derivative. It's a product, x squared times ln of x, right? Bearing in mind that the domain consideration has x needs to be greater than 0, right? So x has to be greater than 0. So we note that, we keep that in mind. All right, so x squared first times the derivative of the second, 1 over x, plus the second, ln of x, times the derivative of the first, which is just a 2x. Clean it up, right? And the idea is that we actually have to do something with this. Horizontal tangent lines, well, a horizontal line has a slope equal to 0. All right, so this would be x plus 2x ln of x, again, where x is greater than 0. So this is an instance where we're actually not evaluating the function. Sorry, I dropped my pen. We're not evaluating the function. What we're doing is we're solving the derivative equation for when the slope is equal to 0. So if I know that the derivative is supposed to be equal to 0 because derivative represents the instantaneous rate of change, represents the instantaneous slope, then I know that f prime of x is supposed to be equal to 0. So I want to solve this equation. So I'm going to pull out an x. It's a zero product property, an algebraic property, which tells us that if you have two factors when multiplied set equal to 0, then each one of those factors individually would be equal to 0. So I'd say x is equal to 0, and 1 plus 2 ln of x is equal to 0. All right, but something to be mindful of, x can't be equal to 0 because of the domain considerations of the original function. X has to be greater than 0 in order for this function to exist. So there's no instance in which x could be equal to 0, so we'd have to ditch that. All right. So then we'd look at 1 plus 2 ln of x being equal to 0, subtract the 1 from both sides, divide by 2, and now I'd be solving ln of x is equal to negative 1/2. So it just begs the question, all right, so how do I get x? Same way we did it up here when we were converting from log to exponential form in general terms. Now we're going to do it numerically. So I'm going to write this as log base e of x is equal to negative 1/2. And I'm going to work my way around. So we'd be looking at x, well, I'll write it the appropriate way. E to the negative 1/2 is equal to x. All right. So it says for what value or values of x does the function have a horizontal tangent? It would be e to the negative 1/2. All right. So I mean, I wouldn't want to do all that work without checking it. So that's what I'm going to do. I want to keep this graph. It looks pretty dang good, so I want to hang on to it. But let's say we have f of x. Oh, I actually already used f of x, right? So I'll just say g of x is equal to x squared. Oh, I need an equal sign. Times ln of x all right, so that's my function. G prime of x would be that red curve, all right? But when you're talking about a horizontal tangent, it manifests itself in a particular way. A horizontal tangent is actually a turning point in the graph, all right? So if you think about like a parabola, the vertex, high or low, same idea. You could actually just pull it visually from Desmos. It just won't give you the analytic response. So it's not going to give you a nice clean answer. It'll give you the decimal form. But if you can find a turning point, you tap on the point that you think is a turning point, it'll present you with a gray dot. If you tap on the gray dot, it'll give you the value. You're just looking for the x value, 0.6065 e to the negative 0.5 is 0.6065. So we're good there. If you don't like that way, what you can do is ignore the original function and set your derivative equal to 0, which is to say, find the x-intercept of your derivative graph, same deal, 0.6065. It's not going to do it algebraically for you, but at least it'll give you a technique by which you can get the answer and at least check your work. All right. So that's where we're going to leave it for tonight. You're going to try those star problems. We'll go over those next class. And then we're going to build up to some more complicated stuff, but not, I won't say difficult. It's just more complicated because it's going to involve other bases. So it won't be a base E. It won't be exponential E. It'll be exponential something else. It won't be a log base E or a natural log. It'll be a log base whatever, you know. So we want to work towards that. And then we'll get into some word problems and then implicit differentiation, which is a pretty fun topic, which is going to lead us into more word problems and then more word problems. Actually, this is the last skill, the concept of implicit differentiation. It's the last new skill of finding derivatives in the unit. After that, we're just going to learn how to apply the concept of a derivative in different ways. All right. So in a lot of cases, that means word problems. And for a lot of people, word problems strikes fear into their very soul, but I'll show you ways to kind of mitigate against that. All right. So let me stop the recording.